So Online Lab 1B is all about interpreting the measurements that you'll make when you're doing the Skill Lab 1A about electrolytes. So we're going to give you some electrolyte data and we want you to interpret it. Let's talk about what we want you to get out of this lab. So we want you to understand what happens to a solute when they dissolve in water. So what is the chemical process of putting a solute in water? What happens to it when it dissolves? And then be able to predict the type of electrolyte from a chemical formula. So being able to relate the chemical formula to the compound type and the compound type to what we expect the electrolyte activity to be, and connecting conductivity to electrolytes. So what does the conductivity measurement have to do with being electrolyte? And finally, we want you to be able to write some net ionic equations of dissolving. You'll also be starting off practicing making some graphs in this lab. All right, so just to back up and remind you about compound type. So for we have ionic and covalent compounds, and don't forget that ionic compounds consist of ions. So they might be atomic ions, like sodium ions or calcium ions or chloride ions, or they might be polyatomic ions like nitrate ions or sulfate ions. So all of the ionic compounds consist of a cation and an anion. And again, as I'm seeing here, we have some examples. So we have a polyatomic cation of ammonium. We have some atomic cations. We also have some anions, so I can take a atomic cation like chloride or a polyatomic cation like nitrate, and I make a compound. So you need to be able to look at a formula and say, I can see that this is an ionic compound. Again, normally we use the rule that typically metal elements form cations and non-metal elements form anions, or if I see a polyatomic ion formula in there, that's telling me that I have an ionic compound. Covalent compounds, on the other hand, consist of molecules and their covalent bonds between two non-metal atoms, or more than two non-metal atoms. So we have hydrogen, oxygen, carbon. All of these have hydrogen, oxygen, carbon, but of course if it had nitrogen or phosphorus or sulfur in there, those could also be covalent compounds. So these are different. They're going to act differently when we put them in water. Also, don't forget from 121, so you need to be able to tell if a chemical formula is ionic or covalent. You probably also should start remembering what ions each element can make. So for instance, iron can make +2 or +3 ions, silver can only make +1 ions, sodium can make +1 ions. So those are things that you want to have at your fingertips, and so start working on remembering them if you've forgotten. And the polyatomic ions, we want you working on making sure you have them at recall, because we're going to be using them a lot. So if you have if you've forgotten them from 121, this is a great time to get comfortable with remembering them. They're going to help you a lot if you can recognize them and remember them. Okay, so let's talk about the conductivity ranges. One of the things you're going to have to do in this lab is to determine from your data. We don't have particularly precise data, so we can't say, there's always a particular range of conductivity that's going to tell us what kind of electrolyte it is. So we do know that non-electrolytes should have no conductivity, and weak electrolytes should have low conductivities, and strong electrolytes should have high conductivities. But it's difficult to place absolute ranges on it. So what we're going to do is we're going to look at the data and determine the ranges from our data. So notice I made a bunch of measurements, solutions 1 through 6, and I had a variety of different conductivity measurements: 13,000, 46, 18,000, 3, 14,000, and almost 1,000, 973. So the first thing I want to do is I want to sort these from the lowest to the highest. So 3 was my lowest one, I'll put that at the top. Then solution 2 was 46, so I've sorted them in order. The next part is to look from some logical breakpoints, like where does it really jump in number? So, do I want to say it jumps between 3 and 46, or is it a bigger jump between 46 and 973? Should I make the breakpoint between 973 and 13,000, or between 13,000 and 14,000? So, there's a pretty big jump from 970 to 13,000. So I think this is a break point here. These three below are going to be very high readings. And now I have to decide, where am I going to draw the line between non-electrolyte and weak electrolyte? And some of this is a judgment call, but between 3 and 46, 46 is still pretty low. Usually under 100 we're thinking is still in the non-electrolyte range. So I'm going to make the break point between 46 and 973. And if I look at the next slide, so I'm calling the 3 and the 46 the non-electrolyte. And then there's a break point, and then the 973 I'm going to make a weak electrolyte, and then the 3 that are in the over 10,000 I'm going to make the strong electrolyte. Now over here I'm assigning conductivity ranges. Now I get to make these up sort of, in other words, somewhere this number here of 100 has to be bigger than 46 and less than 973 to work with my data. And I can, decide it. So I'm going to make it nice and easy. I picked 100. And then for the next one, I said, well, that's anything between 100 and 1,000, I'm going to call a weak electrolyte. And everything bigger than 1,000, I'm going to call a strong electrolyte. These are pretty reasonable conductivity ranges. But again, this is just for this set of data. If I had a different set of data, maybe I might draw the line between weak electrolyte and strong electrolyte at 500. It's going to depend on my data. So your task is to make this decision-making skill of sorting the data and then deciding where the conductivity ranges are going to cut off, and then assigning some numbers to be your conductivity range. So in this case, when I asked in the question, sort the measured conductivities, I would have put my 0 to 100, 101 to 1,000, and 1,001 to 20,000. Okay, so now I want to talk about the conceptual side of what happens to ionic and covalent compounds when you put them in water. If I have an ionic solute, because there's already ions in it, when I put it in water, they dissolve, but then they dissociate. Dissociate means now they're no longer stuck together as positive and negative ions in an ionic compound. They're separated into negative ions surrounded by water and positive ions surrounded by water. So ionic compounds, when they dissolve, they also dissociate into their two ions. This is a major thing that you're going to be doing with your net ionic equations. It's going to be involved in a whole lot of equations coming up in 122. Covalent solutes don't dissociate or ionize when they dissolve in water. They remain as they're intact molecules, but they're surrounded by solvent molecules. We might say they're solvated. We do say that they're dissolved. They're not dissociated. So here I see these are like sugar molecules, and these here are water molecules. And I see over here the sugar molecules are surrounded by water molecules, but they're still intact. They didn't break up like the ionic ones did. Acids are a little bit like ionic compounds. The details are a little bit different. They begin as a molecule, however, when they go into water, they ionize. So the protons pull off of it, and then the protons get surrounded by water and make a hydronium ion. So now, here I had a hydrogen bonded to a chlorine in HCl. Here I have the chloride ions are separated, and the hydrogen ions are stuck to a water, and now I have H3O+. So now we need to talk about the difference between strong and weak acids. Acids are going to be classified as strong or weak based upon how many of the acid molecules ionize when you drop it in water. So if it's a strong acid, they completely ionize. All of the molecules of acid completely ionize and are broken up into anions and hydronium ions, well, protons that become hydronium ions. Whereas weak acids partially ionize. So only some of the molecules of the weak acid break up and form hydronium ions and an anion. The rest of them remain together. And so in general, how do I designate by looking at the chemical formula? We basically have a list of the strong acids. So if it's an acid, I might identify it by ending in COOH, or I might identify an acid by beginning with a hydrogen. Any compounds that begin with a hydrogen are acids in their chemical formula. And then deciding whether it's strong or weak, I'm looking for, is it one of these six? So HCl, HBr, HI, three of the binary acids, meaning there's just two elements in there, and then nitric acid, sulfuric acid, and perchloric acid. So notice that I put a little asterisk. Chemists never really quite agree with each other, so sometimes people just say there's 5 strong acids and they don't include HCl4, and others will also add HClO3 in there as an additional one and say there's 8. So the list can vary, or not 8, there would be 7. But that's a thing that you want to ask your lecture instructor, which acids are they going to recognize as being the strong acids. So we recognize it from its chemical formula, and then we know if it's one of these, it's going to completely ionize. If it's another acid, we assume it's a weak acid, and they'll only partially ionize. So again, just to try and clarify what we mean by a strong acid. In a strong acid, it's completely broken up into hydrogen ions and the anions that were in the original acid. So all of them are broken up. But in a weak acid, most of them remain together. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules that remain together, and this one was a molecule that broke apart. So this one, and then this one is its pair broke apart, and then this one and this one. So a few of them broke apart, but most of them stay together. Usually we use the 5% rule. Typically, weak acids, only 5 out of every 100 or less will break up and ionize. And again, just pointing out, you want to be careful with your wording. Dissolved means that it's soluble, it formed a solution that is homogeneous, and that it is all the things are solvated by waters. But dissociated means it broke up. So dissolve, so for instance, sugar is a covalent compound. It can dissolve, but it doesn't dissociate. So be a little bit careful when you say, oh, it dissociates. Covalent compounds aren't going to dissociate. Ionic compounds and strong acids are going to dissociate. Okay, so how would I write a dissociation equation? And again, these aren't typically, it's not a chemical reaction, but it does help us to sort of formalize what's happening in that picture form and writing it in an equation form. So when I look at iodine, first I have to think, oh, iodine's a covalent solute. And covalent solutes are going to dissolve, but they're not going to dissociate. So all that's changing is the state. It's going from solid to aqueous, but it still remains intact. KBr, well, this is a metal. Potassium's a metal. This is a nonmetal. So this is an ionic compound. Ionic compounds are going to dissociate. So I'm going to break it up into its potassium ion and its bromide ion. HBr, H is hydrogen. I see it's beginning with a hydrogen. This is an acid. I go check my list. HBr is one of the strong acids. So HBr is going to break up. It's going to fully dissociate. So I'm going to make a proton and bromide ion. Sometimes instead of writing the proton, we write it in its hydronium ion form, because as soon as this is formed, it's going to stick to a water and make hydronium ion. HF, well, I recognize it's an acid because it begins with H. I go look at my list. HF is not on the list of 6 strong acids, so it's a weak acid. So it's going to dissociate, but only some of them. So one way to write it is to write that it forms, it dissolves. I have an aqueous form of HF, but then only some of them are going to dissociate. So to indicate that only some of them are dissociating, I'm going to use a double arrow. This is the proper double arrow. In the worksheet, we're asking you to just kind of use a less than sign, a dash, and a greater than sign to indicate it's sort of a 2-directional arrow. But this is the proper way. If we could type it, this is the best way to write the arrow. Then we have KOH. So this is potassium, this is hydroxide. Hydroxide is a polyatomic ion. So really, this is a strong base. Hydroxides are strong bases, but we could also classify it as an ionic solute. So again, they're going to fully dissociate. K+, so I have my potassium cation and my hydroxide anion. So this is what we're expecting you to do when we're asking you to write dissociation equations. just to kind of clarify, when we talk about electrolytes, maybe we should have said this earlier, but an electrolyte is a solution that can conduct electricity because it has ions in it. So the more ions it has, the stronger the electrolyte. So again, those electrolytes have a very high conductivity, usually over a couple thousand, maybe 1,000 is a pretty good range. Above 1,000, it's typically going to be considered a strong electrolyte. So now we're kind of linking, we can measure electrolytes by their conductivity. Now we're linking, yes, but what compound types are going to be connected to what types of electrolytes. So if it's a soluble ionic compound, that's going to dissociate and make a strong electrolyte. If it's a soluble covalent compound, that's going to make a non-electrolyte, right? Because they don't dissociate. There's no ions formed, therefore there's nothing to conduct electricity. If it's a strong acid, they fully dissociate and make ions, so that's a strong electrolyte. But weak acids only partially dissociate, so they make some ions, but not nearly as many as the strong acids. So it's going to be a weak electrolyte. It will conduct some electricity, but not to the extent that we'll consider it a strong electrolyte. Strong bases, so again, those are really soluble ionic compounds, are also strong electrolytes. But don't forget that if it's an insoluble ionic compound, if it's insoluble, it can't dissociate. It dissociates when it dissolves. So if it doesn't dissolve, it can't dissociate. If it can't dissociate, there's no ions. So insoluble ionic compounds are non-electrolytes. They don't really make a solution either. If they're insoluble, it's really going to be, you know, some salts on the bottom of a container of water. They don't make a solution. But if you were to measure their conductivity, you're going to get a very, very low reading, a non-electrolyte reading. So you need to be able to identify from the chemical formula if it's ionic, covalent, or strong acid or weak acid, and then identify which type of electrolyte it is. So again, we ask you at the beginning to determine the expected type of electrolyte from a chemical formula. So we'll use this set of samples. So iodine is covalent. This is two nonmetals. KBr is an ionic, a metal and a nonmetal. HBr is a strong acid. It begins with an H that tells me it's an acid, and it's one of the 6 on the list, so it's a strong acid. HF is also an acid, but it's not on the list, so it's a weak acid. And anything with a hydroxide anion, an ionic compound with a hydroxide anion, is a strong base. We could also have classified it as ionic. And now I just match it up. When we know covalents are non-electrolytes, ionics are strong electrolytes, strong acids are strong electrolytes, weak acids are weak electrolytes. Finally, you're going to need to make a graph and find a trend. So to make the graph, you're going to make a table with a column for the molarity and a column for conductivity, and put the molarity on the x-axis and conductivity on the y-axis. We have some provided videos if you need help on how to make a graph in Excel or Sheets or in Logger Pro. You can also, your instructor may allow you to do a manual graph as well. And you're going to want to add a trend line. Now when you add the trend line, it will ask you usually, if you're doing it in a program, if you want a linear or a polynomial or a logarithmic. The first thing is you're going to look at the dots on your graph and kind of decide, is it a line or is it a curve? If it's a line, choose linear. If it's a curve, play around with the polynomial, logarithmic, exponential until you find one that looks like it fits well. Or maybe it has no pattern, in which case you can't add a trend line. And then I want you to think about what the molarity is. What did we define molarity is? And think about what causes a solution to be conductive, and talk about that trend. So whatever trend you end up observing, if it's a curved pattern, try to, an exponential, does that make sense in terms of conductivity, in terms of the ions? So you're going to be tasked with answering these questions. If you have further questions, feel free to email your instructor and get more clarification.